Hi everyone, and welcome to the fourth in our webinar series, Connection Regardless of Location. This session will focus on metro coverage. My name is Sam Dilley, and your speaker today will be Stuart Stevens, one of our senior systems engineers here at Axell Wireless. We've got a very interesting webinar today, but before we start, I just have a couple of housekeeping points to make. During the webinar, you'll be placed on mute to avoid any feedback and to help ensure we finish on time today. If you have any questions for Stuart, please send them via the chat option, which you should see on the right-hand side of your screen, and we'll get through as many as we can at the end of the webinar. Okay, over to you, Stuart.
Thank you very much, Sam. So we're going to go over our metro presentation. So first of all, we'll go over a bit of an introduction on Axell Wireless, then we're going to go over why metro coverage, then we're going to go over solutions for metro coverage, and then we have a case study. So a quick introduction. Who are we? Axell Wireless is a global developer and manufacturer of DAS and wireless coverage solutions. We are part of Cobham PLC, which is a global technology giant worth $3 billion annually in revenue. We provide solutions for cellular, public safety and railway applications. Our history spans for over 40 years because we are three companies that have merged, and our focus is on quality and technical innovation. We've got customers in over 150 countries, including 170 mobile operators, and in most of those countries we've had experience with metros and public safety applications. We operate from 16 offices worldwide, and we have around 250 employees, which is growing on a daily basis. The latest AIB research reveals that Axell Wireless is now the #1 for innovation when it comes to in-building wireless technology. We have some very nice new products which will be launching in the near distant future, going to new evolutions in digital technology. We are ranked 3rd globally overall in terms of implementation and market share, and this year we are expecting to grow our market share by another 20%. And this has continued to grow, which it has for the last 5 years. So going back to our topic for today, which is why metro coverage. Nowadays, commuters are expected to use their mobile phone or tablet wherever they are, and this includes the underground metro system. If you've got a monthly contract, you expect to be able to use your data, especially in a foreign country. It's also, in the event of an emergency, the emergency services need to be able to communicate with each other and the staff themselves, which will mean the metro needs to be able to run and maintain its constant reliability. The transport operators need to provide radio communications to the staff and drivers. In fact, we experience quite a lot of the wireless systems actually running the trains as well, with train radios, both for digital and old analog systems. Metros are not just the tunnels, you have to think about the ticket halls and the stations as well. And in the extremely high peak times, especially here in London, we have massive peak demands of traffic. Again, for the traveller, we know this down to better uses of time while travelling or waiting at the stations. Interrupted connection to the outside world through voice calls, text and internet, and a safer travelling environment. People now use their phones on apps to get real-time information if the trains are going to be delayed, what train they want to catch, working out where they're going to go. For the mobile operator, it's all about customer satisfaction and experience. People want to know that they're paying a lot of money a month now, and it's quite a big utility bill, and they want to know that they can use this. It also means they can get revenue from premium standards and roaming customers as well, because it increases the uses, because when you're abroad, you're not sure where you are, you want to get data from where you are. And again, if you look at this from the actual people who run the metros, customer satisfaction is very high. For them, it's more about the public safety side of it, about safety, the police, emergency services, and also the staff. And it's also nowadays, it's a portal, because it's able to offer the customers an experience about what's going on in the metro, any deals that can be used locally, and an advertising base. So how do we achieve this? we normally think of metros in two areas, and that's the station and the tunnels. In the station, we have normally a limited space, so we have to find somewhere for the equipment to be stored. And sometimes we've seen some very, very complex structures. Sometimes the entrance for the metro can be, you know, almost a kilometre or 500-600 metres away from where the actual tubes are. And again, in some of the older metros globally, some of those stations are now actually listed buildings. So installing that can be very, very hard. Demands for the capacity of the system in those areas are also key, because there can be, especially at peak commuting times, a lot of people in one area. In the tunnel, space is very, very limited, and sometimes also you cannot actually install the equipment in the tunnel because of safety fears. The worst case of this is actually here in London, where the tube is the diameter of the tunnel itself. So the trains, and there's no space for actual equipment inside the tube areas. Also the varying lengths of tunnels. So in the city, they could be only 500-600 metres between stations, yet more outside rural locations, there can be up to 2-3 kilometres between stations. There's normally more of a low capacity demand in the tunnel because people are constantly moving, and when you're going along, not so many people are sitting on their phones and tablets. So the solution of how we do this is for the actual buildings themselves, the stations, we treat them more like an indoor building application, where an optical DAS or distributed antenna system receives a signal directly from the base station hotel and is distributed. We have seen many applications where not only is the station used, that above the station there's a shopping mall, a hotel, there could be offices. So we use the same system in that particular area to not only feed the covering of the sections and the maisons and the shopping hall, it will then go down to the tunnel. We also, having received the radio signals, we can filter it throughout the buildings and ensure maximum coverage. This means that we can also have the cellular system maybe going into the buildings, but keep the public safety system more for the texture inside the tunnels. In the tunnel itself, we always go for a BTS Hotel type application, and then we use a DAS system throughout the tunnel. We always recommend leaky feeder cables, although antennas have been used, but we recommend leaky feeder cables. The DAS receives a signal from an external base station, and then this is then fed via the BTS Hotel. We often get asked what is the typical range between the remote units or the BTS or the remotes inside the tunnel. We try to have around 800 to 1.2 kilometres between each remote unit. This is roughly our rule of thumb working out. So if you're trying to plan how many remotes you need on the metro. So this just depends on the number of carriers, the frequencies you're using, and whether you're doing a joint PMR/cellular application. Dynamic capacity is quite an important subject when we're talking about metros. Now this is more for a cellular type application. And if we take London Underground as an example, so roughly we have 3.4 million passengers at peak days. And this is normally 1.7 between the commuting hours of, in the morning rush hour and the evening rush hour home. And that works out to be 100 passengers at the same time. And that's with an average of a 20-minute travel duration. So if you take that down, and this is only for a 2G system, we're not talking 3 or 4G here at the moment because we don't have that sort of information back yet. This was done on a 2G application. The demand there is 3,000 ELANs or 70 sectors of an 8T or XL. Quite a high demand. So if we look at this in two ways, of the BTS sector, so if you deploy a BTS at each station, each 12 sector BTS could have an equivalent of 8.1 ELANs per application. However, if you go to a BTS hotel approach where we have an optical DAS distributed around the same station, And because that DAS capacity is distributed around, at any actual station, there could be a 35.2 ELAN potential at each station. What this offers us then is, if you look at it in the table below, effectively a total base station application there of 97.2 ELANs, yet with a repeater solution you actually get more ELANs percentage because it's distributed around a greater area. So the cost is a lot cheaper because you don't have so many base stations, yet you actually get better responsibility. This is what we call trunking gain. It's where it's more efficient, and this is where DAS systems in metros come into their own, and why most applications and most metros we know globally go for this type of application. So if we look at it in a point-by-point basis, with a fibre optic based system, capacity from the BTS is available at all repeat locations. And with a BTS system, the capacity is limited by the base stations at each station. The also big downside to that is, if you're going to upgrade to an LTE system, rather than just having a BTS Hotel to add the base stations to, you'd have to upgrade and fit a 4G base station at every single station around the metro. Whereas if you had a multi-carrier base repeater, you only have to upgrade one area and it will go down the same system. And if we just highlight comparing the two systems with a 2-carrier BTS location and a 3-section BTS Hotel with 6 carriers, every 2 carriers there is an ELAN availability of 8.1 at every station, and with a sectorized fibre optic system there's a 35.2 ELAN capacity available at every station. So effectively, it's up to 4 times more capacity could be available at the application. And if we summarise it, BTS is a high space requirement, especially for multi-band multi-operator, and there's a large amount of time and effort to provide a multi-operator service, and it's got very, very low trunking efficiency. From a fibre optic repeater perspective, all operators are combined in one relatively small cabinet. It's a very low power consumption. It's a single RF port for all services, and capacity can be distributed to several repeaters. And this is what we call the BTS Hotel concept for optimized trunking efficiency. The actual side effect of this, which a lot of people don't realize, is that because this distribution is, because the BTS Hotel is being distributed equally around all stations, it means that the capacity is everywhere where you need it. So without having to realign the base stations or realign capacity, at the weekend, if one of the stations is near a football match or some sports event or a theatre, the capacity is there where it needs it. Yet at the weekday, it could be the capacity is needed near office blocks, high demand, high public places. So without having to do anything, you don't have to recapacitize, reset up your capacity. It's naturally going to be there because the same capacity is everywhere. If we look at a capacity sharing and efficiencies and how you can sectorize up a BTS hotel and how you can sectorize up a metro system, you could have it so in the more densely populated areas in the city centre, you may have up to 5, 6, 7, 8 sectors, or almost a sector per station because of the high demand there. Yet out in rural applications, we can stretch one sector to maybe cover 4, 5, 6 stations because there's not so many people. And as they come into town, there's more capacity needed. It also means that higher operators who have more subscribers, who have more people involved, they have more time and more capacity, so they can add more sectors and more base stations, where the smaller operators can add less base stations but still get the same coverage. So every operator can select every sector size, and that's a very key important. This is very significant because the CapEx and optic savings are huge due to the trunking efficiency, and that's what the operators like. Now this is an overview of how a system would look, and here we're showing both public safety and cellular. Public safety is probably more used in a lot of metro systems because public safety, as well as old-fashioned VHF low-band and high-band systems, and nowadays Tetra and going forward new LTE Tetra, are used to run the trains and of course with the police services and public and emergency services on the systems. So our systems are designed not only to do the cellular, they're very much based on public safety. We've developed a POI and a master site that can pass both PMR and cellular, and they work together on one common system. This is a typical Axell Wireless architecture for this setup. We have a POI. Now this point of interface could be for cellular, could be for Tetra, public safety. We custom build these depending on what the application is and depending on what the requirement is for that particular metro system. We then can split our optical master units on the same common platform, and we can mix and match between different technologies. So you can have a Tetra unit, or what we call a BSF 3604, or we have a BSF 3602, and we have a high power MBF 40 unit, which is more based on cellular applications. So if, for example, you don't need as much remote units for the PMR public safety because the loss of the cable is better at that frequency, you don't have to have as many remote units for public safety as you do for, say, the cellular, or vice versa. It's also a plug-and-play system, so if there's any, as the metro expands and they build more stations and expand the network, you just plug more modules in to cope with how the metro changes. It's amazing how we see how many more sectors are added as more people move and as populations migrate and different applications get used. In the tunnel, like I say, we only use radiating cable. I have seen a couple of metro systems run on antennas, but there are some issues with that and it has to be very, very, very well balanced. So we normally go for a radiating cable. Radiating cable technology has moved on a lot in the last years, so you can get both cellular and public safety down the same cable, although sometimes we do see separate cables because the PMR prefer to have their own infrastructure which is not used by any MNO. However, normal application, we have a shared infrastructure with radiating cable. We then split or crossband coupling both units together, and both boxes sit side by side to give you both the VHF and Tetra and GSMR application. Sometimes we have 2 boxes, sometimes 4. It all depends on what the requirement for that particular environment. Now, the difference between a public safety system and a cellular system is that for public safety, redundancy and 100% proof of operation are key. So normally we would take an approach where we'll have 2 base stations stored in 2 different parts of a city or town with 2 completely independent fiber backbones feeding either independent or separate remotes feeding 2 parts of a tunnel. This means that if any base station fails, if any fiber fails, if any remote fails, due to the unique setup, you still have coverage. Sometimes this is doubled up by having 2 remotes at each location too. The difference is on public safety is it has to work if there is an emergency or the trains have to run. So therefore the design has to be foolproof no matter what happens, and this is how we do it by having 2 independent systems. Yes, there's a cost implication here, but when it comes to public safety, we see most systems are put forward like this. Now, the BTS Hotel design concept has been used for a while now, and it all started from metros and stadium type applications. We combine all the base stations and all the capacity in one location, and the BTSs then feed the OMU, which is converted to a fibre and then distributed down the railway track to a number of remotes. We can feed a lot of remotes from a BTS. It's typical for metros to have 1 to 200 remote units. That is common. You normally have 2 to 4 BTS hotels. So you don't have to have 1, it's normally split. Then if there's a power failure or something happens at a location, you've got the coverage distributed around. We tried to have the BTS hotels away from the railway itself. This is only because of trying to get access to work on a metro is extremely hard. It's normally only night shift hours or weekend access, and sometimes the windows can be only 2 to 3 hours before it has to be repaired or replaced. Therefore, by having the BTS hotel not trackside and in an accessible building is the best application. And this is why we normally have 2 or 3 remote sites in a station where access is available or in a building that is owned by the metro operator. Base stations of a number of sectors and multiple standards can be obtained in the BTS hotel. We normally see that the public safety and the GSM is put into the BTS hotels. Sometimes with 2 doors, one for the public safety and one for the cellular. But by doing this, it considerably reduced the OPEX and COPTEX with savings in space, power and cooling. Again, we're going over the multiple access by multiple parties to allow it to replace, and this is also for maintenance, of course, because having to get involved in highly restricted access areas. We always monitor metro systems. This is mainly more for the PMR because, of course, if you're running the trains or if you're running different users of applications, we monitor the remotes. We can turn off sectors, add sectors. We can look at the noise in the tunnel. We can interface and engage what's happening to the repeaters and what's happening in the areas. So we always have a very easy to use GUI, and we always recommend monitoring. So this becomes part of the metro's network. If you're going to invest in a system like this, let it help you to see what's going on with your network and enable to make sure you know what's happening and you know what's going on with a customer experience and that you've got coverage working. I'm going to go over a case study now. This is Washington Metro. So we've been working with the Washington Metro since back in 2005, and we've been working very closely with WMATA, and this is to support an ongoing legacy coverage system. And this has also been supporting the design and also the supplying of equipment. This is mainly a public safety type application, and this is where they have 2 systems in the UHF band of 490 MHz, and also they run an 800 MHz public safety radio band as well. And this means they have to ensure radio coverage in various challenging environments, and that includes the underground metro itself, but it also includes the stations. And for them as well, they have a large amounts of parking, dockyards, and also quite weird buildings that are all run by the same authority. And the challenge was they had to have coverage everywhere. Now, one of the things that was inherited was a very old 490 MHz line amplifiers that had to be replaced because they were obsolete. So to start off with, Axell custom built them a replacement 490 MHz line amplifier, which was tailor-made to be a drop-in replacement for what they had. Just to start them off and to keep the system going, we just had to replace what's there. Then moving forward, we had to channelize the repeaters to stop the amount of noise that was being generated by the line amplifiers. And this was the first time Axell developed its DSP technology, or digital signal processing. And this allowed us to get a better infill coverage into many of the parking areas and the stockyards. We then moved on from that and put in fiber fed repeaters for coverage in the stations and along the New Dallas corridor network. And this is a dual system for 490 as well as the 800 megs. We developed a special system which was custom built to do both the UHF and 800 megs. So this was started off with old line amplifiers and upgrading it to a completely modern fiber optic based system. We call it out with the old and in with the new almost. In the end, we had a redundant head end for both 490 and 800 MHz systems, incorporating the DSP technology and incorporating a noise gating system. And this allowed for a much better balance and improvements of noise levels. It also generated from the legacy fiber optic remote system, and it was constantly improving the dynamic range of the coverage. As the system moved over to the new system, they were constantly seeing better and better improved coverage areas and less noise, enabling a much better overall performance. Also, because it was completely redundant and was using the latest technologies, we offered a much better mean time to failure. And the engineers reported where they're having to go around every night trying to hold the system together, all of a sudden the radio system was just working and it was no longer becoming a day-to-day problem for them. The benefit is improvements made with the WMATA communication system is increasingly flexible and future-proofed against technology's upgrades, and improvement to the legacy kits are necessary to keep passengers and staff protected. I hope you found that interesting, and I hope you found it informative. If you do have any questions, I'll be happy to take any that may be sent through. I'll do my best to answer what comes through, but I do sometimes get some quite weird and wonderful ones.
Thank you very much, Stuart, and thank you everyone for listening. We have had some questions in, so I'll get right on to them. What is the maximum distance a fibre fed repeater can cover in a tunnel?
Okay, I briefly covered it in the slide, but it is one of those subjects that always come up. It really is down to the antennas, or in this case, leaky feeder cable you're using. And if you install a high quality leaky feeder cable, up to 1 kilometre can easily be achieved. We're facing more and more challenges though, of course, with the new 4G systems because of the 2600 meg band and the high loss you see on a leaky feeder cable. But if you're doing a budgetary quote or want to work out how many you need, if you took 1 kilometre as a kind of a starting point, you won't be far off.
Okay, thank you. How do you combine the cellular and public safety services together in the tunnel?
This is a big question that comes up often, and we have to use special filters. Sometimes you can't just cross-band couple a system together because PIM can be an issue. We have a range of combiners that we use and are tailor-built to every single metro application. There's no really one-box-fits-all for this application. So you will have to use good quality, low-loss combiner filters. Again, there's no point installing an amplifier then to lose all the power through high-loss combining. So we don't try and use hybrids because of PIM issues. So we build custom-built filter band combiners to combine them both at the same time.
Okay, that's great. Right, we'll come to an end there. If you haven't had your questions answered, we'll follow up by email. But if you do have any others, please feel free to send them to Stuart. His details are on the slide in front of you. We hope you enjoyed the webinar, and we hope you'll join us for the next one. Thanks a lot.
Bye.